Hello and welcome to Toddcast number 41. So this is continuation from 40. We're going to go a little more into addition reaction. We're going to talk about the regional selectivity, which we introduced that term as the selection of one carbon as opposed to another on a molecule when you react. And then going to go into a little more depth in terms of Markovnikov and then ultimately anti-Markovnikov addition. So Markovnikov addition, if you recall, is where the first group on, in the examples we gave involved a hydrogen, went to the less crowded or the more spacious carbon of the double bond, leaving the second substituent, whether it was an OH or BR as the ones we looked at, going to the more substituted. And so we made a declaration that H went to the side that there were more H's on, and used the phrase Gumpnikov, as in Forrest Gump's famous phrase, H goes where H is. And so we're going to continue on that and talk about why some reactions actually will start going in anti-Markovnikov fashion. So with all that, I want to start with symmetric versus asymmetric alkenes. And we're going to start with symmetric because then there's some sort of balance. And so when I'm evaluating how the reaction is going to go, I'm going to first consider the double bond, these two carbons here. They each have an ethyl and an H, an ethyl and an H. So the double bond itself is symmetrical. Same things on both carbons. The HBr is asymmetric. So if one is asymmetric but one is symmetric, generally we don't have an issue. So whether this H goes on to the left or right side, so I'm going to draw intermediates. The H goes on one side, leaving a plus charge here, or whether it goes on to the opposite side. There's no physical preference. There's no steric hindrance forcing it to go one way or the other. So in the event the H adds to the left carbon, we'll find the Br on the right carbon. In the event the H adds to the right carbon, then we'll find the Br on the left carbon. Okay, because of the symmetry, the inherent symmetry we have in this molecule to begin with, then this used to be the double bond, has an H and a Br, ethyl and ethyl on each side. The Br, either way you cut it, is going to be on the third carbon from the end. So if you recall, you number in a way to try to give the smallest possible number to the substituent. So 1, 2, 3. Whereas I'd number 1, 2, 3 from this side, making both of them 3-bromohexane. You get the same compound. So if your molecule is symmetric, by molecule there's two involved, either the alkene or the group being added, then you generally don't run into any issue of multiple products being formed. However, all that's going to end because in all likelihood we'll be adding something asymmetrically to an asymmetric alkene. And so consequently, we need to look at that a little more carefully. So you end up getting regioselectivity or regioisomers, the result of the substituent going on one side versus the other. We're also going to eventually get stereoisomers from this, but for now it's considered regioisomers. So in this case, we have an asymmetric alkene right here, this double bond. So this double bond here has a methyl on one side and has 1, 2, 3, so a propyl group on the other. So when I add to this one, the methyl versus the propyl, they're both disubstituted. So the overall alkene's disubstituted, but both have a methyl or an R group and the double bond. This has a propyl in the double bond. So they're equal in that sense. So again, the H could go on the first or left carbon, this one, or it could go on the right one and end up here, which would mean the bromine will end up on either carbon 2 or carbon 3. So these are regioisomers. There's a stereocenter that's been formed at each case. So there's an H in back or in front. I'm not drawing the specific stereochemistry here, but you would have a methyl, a butyl, an H, and a Br. So you will end up getting equal parts RNS. You'll get a racemic mixture of 2-bromohexane. And then from this other molecule, we'll get an ethyl, propyl, an H, and a Br. So we'll have a Br, H, ethyl, and propyl, ethyl here, propyl here. So for unique substituents, we would also get 2 stereoisomers here, racemic mixture. But we're worried, at least for the time being, just with the ratio selectivity. So whether the BR goes on the left side or the right side, this is what we'll end up getting. There will be a slight preference because methyl is smaller than propyl, so we'll probably see this depending on the temperature we do it at, maybe 55-45, 60-40, something of that nature, but it won't be substantially one more than the other. However, in the next case, where the alkene is on carbon 1, between carbons 1 and 2, I should say, then we have a definite competition that's going to favor one side over the other. The left side in this case has two H's. So by having two H's, as opposed to the other side, it has one H in a bulky R group, the butyl group, the HBr is now going to have a definite preference where the H goes on to the less crowded side, H goes where H is, so two H's here, one H here. So I will more often than not see the H add to the end as opposed to the H adding to an internal carbon. So again, this will be temperature dependent, what percentages we get, but it will be substantial enough that we can actually define one as a major product, one as a minor product. So I'm going to just toss 80-20 out there, might be 90-10. Again, depends on the temperature and the conditions and the solvent and other factors, but we're going to definitely favor this one. So the so-called Markovnikov addition, where Br ends up on the more substituted carbon, as opposed to the anti-Markovnikov. These, they're both technically Markovnikov because it goes to the more substituted, but there is not a more substituted carbon, so we just don't bring it up. This one, there definitely is the distinct Markovnikov, which I'm just going to write Mark, and anti-Markovnikov. And our preference will be Markovnikov addition. Okay, so rehashing those terms, I want to look at the competing mechanisms for the two products we saw. So I want to consider this double bond again. There's one, two H's here, and one H here, one, two H's here, one here. So in each case, I'm going to add HBr, same as before. The double bond is going to go out and get it. So notice this is sort of arcing this way. So because the arrow is arcing that way, that means the double bond is swinging out that way. I'm going to leave a plus charge here. This one's swinging out this way. It's going to put the H on here and leave a plus charge on the first carbon. So it's subtle, but this one's swinging out in such a way that this bond stays intact to carbon 1 and breaks at carbon 2. So when H goes on 1, leaves a positive charge on 2. This one swings out this way, replacing H on 2 and leaving a positive on 1. Okay, depending on how this works, and you do get a lot of chaos in the reaction, this plus can rearrange from secondary to secondary to secondary to secondary to secondary, so it could move up and down the chain. And we'll never really know if it goes all the way over here, whether it add here or here. Might get BRs here, might get BR here, but for the time being, let's consider this isolated intermediate. On this side, primary is probably going to rearrange. So even if I did do this addition, rearrangement would be fast enough before the BR came in that you're not going to get a lot of this product, but you will get some. So secondary carbocation, more stable intermediate, primary, less stable intermediate. Rearrangement, even if the H went on here and left the positive charge here, it will move over quickly. The BR is now going to attack. It's going to attack that carbon and this carbon. So the BR minus is going to attack the positively charged carbocation. And you're going to end up with the more substituted product, the so-called Markovnikov, and the less substituted, the anti-Markovnikov. So we have my Mark and my anti-Markovnikov addition. Okay, so pretty straightforward. So major and minor. You want the more substituted carbocation, which can lead to the more substituted substituent being added in the final product. So Markovnikov addition. Again, I want you to get used to saying that. No pride whatsoever. So if you hear that phrase, H goes or H is, then you know what that means. H is going where it is. Okay, so again, let's consider an asymmetric alkene and an asymmetric reactant. This carbon, two R groups, this carbon, just one R group. So H is going to go where H is. There's more H's on the first or left carbon than there are on the second or right carbon. So 1H versus 0H, H goes where H is. So you will end up getting the H on what's going to ultimately be carbon 2 of the chain and the Cl on carbon 3. So first, H goes on first, so it chooses the better seat, if you will. So H is going to go to the first carbon, it's going to go to the second of the double bond, or second and third in the chain length. However, once I add the Cl, then the priorities are going to change. So actually, this is 1, this is 2, this is 3, this is 4. So carbon number 2 is going to get your Cl, carbon number 3 is going to get your H. So 1, 2, 3, 4, chlorine's going to go on in that spot. So it gets stuck with the worst seat, if you will. And the reality is this Cl will go on anti to the bulkiest group over here. So I probably should, to be a little more precise, draw it with dashes and wedges. So the Cl is going to come on top. Those used to be trigonal planar because of the MTP orbital sp hybridization. When the Cl came on, it went up. And it will want to be anti to the bulkiest group on the other carbon. And so I'm going to make one of these H's arbitrarily red. In reality, it could have been either one. It could go on either side. Okay, hopefully that seems okay. Seems reasonable to you. And in fact, you know what? I'm going to stay true to the picture above and actually make that one, because if it rotated, this would match. This came down, CH3 went in the plane. So just to have that match there. Okay. So now we're going to play identify that reaction. So you will need to be able to decide quickly which substituent went where. So when we add water in the presence of acid, H0 plus, strong enough acid, then you're going to add an H and an OH, it's going to be hydration of the double bond. H goes where H is. So this end of the double bond, there's two R groups, this end, an R group and an H. So 1H and 0H's. The OH ended up, the 0H side was, so Markovnikov addition. So let's look at another one. For this reagent, this combination, so instead of using H plus, we're using mercury acetate. One of the acetates comes off readily and mercury becomes +1. So it's acting just like an H plus, except much bulkier, and it's able to coordinate electron density, so it can actually hold the position to prevent rearrangement. NABH4, you briefly encountered this concept, like rich in H, when you did oxidation reduction chemistry and general chemistry. So if you have something with lots of H's, it's typically a reducing agent. So this is going to reduce the mercury away and replace it with an H. Okay, we'll see that as it goes. This side, two carbon groups. This side, one carbon group and an H. So 0H is 1H. So the O ended up on the carbon with 0H's. So the H ended up on the side with 1H. H went where H was. So H ended up where there were already more H's. So this was Markovnikov addition. Okay, so let's see what happens in the next one. HBr with peroxides. And so again, we're going to go into these mechanisms down the road. For now, I just want to identify where things end up. The left carbon has two R groups. The right carbon has two H's. The Br ended up on this carbon right here. So it ended up on the less hindered this time. So H actually went to the side where there were 0 H's. So H went to the 0H side. Br actually went to the 2H side. So H didn't go where H's were. So it did the opposite. So H went where there were less H's. Really want to emphasize that, less H's. So we refer to that as anti-Markovnikov. And so again, go through the mechanism. Your job for now is just recognize. And one thing that, if you start seeing a pattern here, you should note peroxide and peroxide. That's going to be one of those key things. Peroxide must be doing something really weird, because in both instances, so in this case, 1H here, 2H is there, and the H is going here, on the 1H side, the OH is going here on the 2H side. So H is going where there's less H's. So once again, it is anti-Markovnikov. It goes where there are less H's. This one went here. This one went here. So when there's peroxide involved, we end up getting what's known as an anti-Markovnikov product. Other pathways, we typically get the Markovnikov. So again, we'll look at each individual reaction. So there's 4 reactions. We're going to look at it in detail. We kind of looked at the first one, a little bit of detail, but we'll go in a little more as we go. But you'll start seeing then that we can target, we can create our reagent combination as we wish to get the result we wish. If we want Markovnikov or anti-Markovnikov, we can adjust our reactants. So here we have an alcohol that's Markovnikov. Here we have an alcohol that is Markovnikov. Here we have an alcohol that's anti-Markovnikov. Here we have a HBr that's anti-Markovnikov. Earlier we did one that's Markovnikov. So we have different ways to generate whatever product we want. Important to recognize that skill is going to be very useful. Okay, so in pure hydrogen halide, HX, HCl, HI, HBr, HF, HF's terribly weak and probably not going to work, but your stronger acids, HX will. Is using electrophilic addition alkene, it follows Markovnikov's rules, okay? Meaning H goes on first, H plus, H goes where H is, goes to the more available seat, the better seat, leaving the X to get stuck on the more crowded seat. So we consider the double bond. Got an H on this side, no H's over here, so this is a less crowded. There's already an H there. So you're going to put the H on here, leave the carbocation on a tertiary site. The Br will eventually come in. HCl, H goes where H is, 2 H's here, no H's here. So I'm going to see the H added to that spot and a positive carbocation at a tertiary. And then finally, again here, this ring system, we have 2 R groups on the left carbon, only 1 R group, the methyl on the right, methyl small on top of that. So H goes where H is going to go less crowded, going to leave, again, a tertiary carbocation. So in each case, we're dealing with a tertiary carbocation, which is nice and stable, relatively speaking. So now it's just a matter of the Br coming in, the Cl coming in, and the Br coming in. So the Br will come in the first one. You'll brominate at the tertiary carbon. Chlorine will come in, you'll chlorinate at the third tertiary carbon, excuse me. And then last one, you'll brominate. So there's not much to this beyond everything we've already been doing. And this is just a case of the more exposure, the better you'll understand it. So the more you look at these reactions, the more you get used to doing a certain systematic approach. You know, it's an addition reaction because it's an alkene and a strong acid. H goes where H is, first thing to consider. So H will go to the less crowded side, leaving the positive on the more crowded side. And then it's just a matter of adding the other group on. In this case, it's a Br, a Cl, or a Br. If we have water, then it'll be an OH. So we'll get into a few more details as we go. Okay, mentioned also in the last podcast, the concept of syn addition versus anti-addition. And this leads to something along the lines of stereochemistry. So I alluded earlier when we looked at this one, this compound, this 3-hexene trans, even if it's cis, I'm going to not worry about it quite yet, because it's a achiral or symmetric alkene, we're not going to get any optical activity. So as mentioned before, sometimes the H will go in back, Br will come in front, sometimes Br will go in back, H will be in front. So if I do the chiral analysis, this is Br in front, it's priority 2 here, priority 3. So 1, 2, 3. H is in back, so this is an R. And then over here we have priority 1, 2, 3. But H is in back, so it's an S. So we have half R, half S, which means we'll get a racemic mixture. Alpha D is going to equal 0. Okay, so fairly important to recognize there's radial selectivity, which carbon is the H going to go to, and which carbon, therefore, is the other group, the other substituent, going to default to attacking. And then when it does attack, you get stereocenters. Okay, so racemic mixture is pretty common with dealing with alkenes. Now we have a far more complicated chiral situation. We have two rings, neither of them terribly strained. Six is fine, but with an alkene, it's slightly strained. Carbon ring, typically fine, but will be a slight strain because of the sp2 carbon. And then 1, 2 chiral centers for sure, and a soon potentially to be chiral center here, and maybe even here. So it's going to be a little more complicated. H goes where H is. So H is going to want to go to the less crowded side of the double bond, leaving Br to be at that bridgehead, or this point. We have the two here. It's a chiral reactant, meaning the stereocenter here, stereocenter here, they're stereo pure. So as a consequence, the alpha D optical rotation is not zero. It does rotate light. Don't know which way, they don't tell me that, but I do need to recognize that this solution is optically active. So we've done nothing to change that. We've done nothing in the reaction to get rid of these chiral centers that pre-existed. So Br is going to go in back and in front. One note of interest that I'm ignoring here, a regioselectivity issue. When you get the positive charge right here, so when I add the H, let me just draw that briefly. Let me get rid of that double bond and put on the H that's added from the HBr and that positive charge there. You can get rearrangement. So the H here can migrate across and the carbocation could go there. You may end up with the bromine down on the other tertiary carbon. I'm ignoring that for now. So I'm focusing strictly on the stereochemistry of the double bond as we see it. This time, the Br in back is actually to be a little bit better off because these two groups are in front. So the front face of this molecule is more crowded, so it's easier to come in from the backside. Br to come in from this side would have to interfere with those two groups that are sticking up. How much and what the temperature is, those are both going to factor into what percentages, but not unreasonable to expect a 70%, 30%, 75%, 25%, some ratio like that, where a major product and a minor product are formed. Okay, we call them diastereomers because, quick revisit, 1, 2, 3 chiral centers, 1, 2, 3 chiral centers, same, different. 1 out of 3 change. It's just some of them, not all, so it can't be enantiomers, but it is at least one, so they can't be identical molecules. They're stereoisomers because they have at least one change, and the one change makes them diastereomers. So diastereomeric mixture, a major where the bromine comes in back and avoids the bulky groups, minor where it comes in front. And again, percentages, I'm not going to worry too much about them because short of giving you exact temperatures and exact solvent conditions, you can manipulate that distribution. Just know that the bigger amount will be here, smaller amount there, and it's going to be anywhere from 2 to 1, 3 to 1, 4 to 1, depending on the conditions. Okay, so this goes into the anti-Markovnikov and Markovnikov. We didn't really go into mechanistically what causes anti-Markovnikov. We went into far more of the Markovnikov perspective, but we're building up this pool of information and going to get back to spider charts soon, where we're going to start writing all the reactions in a cyclic fashion, because you must memorize not only the reaction, but the stereochem and regiochem nuances of it. So thank you for joining in, and I will end this and see you at the next podcast. Bye.